today I'm going to share with you few idea about how can we deal with charge compensation mechanism in our daily life. Our business is always is dealing with ionic electronic charge transfer in the materials. And when I sent the first abstract to Christian, he said, "Are you know that you are going to give a talk for post-lithium?" Because what my talk for was more in lithium. But I found a way how can we learn from few studies in post-lithium batteries. Okay, let's go to the schema that yesterday Jürgen showed here about how can we rethink about charge transfer not as a punctual transfer process, but is more like collaborative transfer process. But the missing picture here in this schema is what is the ground rule of the host bath. I mean, this is the bath that will host this charge. So this bath will fix some rules for the players. Some of those rules we learn in the high school or in the university are Pauli exclusion principle, Hund's rule, degree of correlation, and so on. Those rules, there is this is what we call a primary rule, and there is also secondary rule when those collaborative process occurs, which are crystal field splitting, ligand ionicity, electronegativity, and so on. But we should not forget that this process is dynamic. There is a charge, discharge, so will impact other processes like phase transition, Jahn-Teller distortion in some systems, disproportionation in some chemical structures, loss of ion displacement, ordering, metal dissolution, SEI, so on. So how can we learn from two kind of technology, lithium and magnesium batteries? Let's go to historical background for lithium. We start with titanium sulfide in the beginning for Whittingham works, which we can insert and de-insert irreversibly in titanium sulfide. But the fact that sulfur 2p orbitals low higher in the bonding state, that's lower the potential. So we went to more oxide based with a lot of success. And we have several families like layered, spinel, olivine, and so on. Going to magnesium, people try to duplicate the same process. Historically, we learn from what we duplicate what we learn, and the first successful material is what we call Chevreul phase, and that will be the main of my topic. And then we went for spinel, titanium sulfide, and sulfur. But once we make the jump to the oxide, we face to the strong ionic character of magnesium-oxygen bonds, which bring a new philosophy of how can we deal with this strong correlation by screening this effect. But people, they try with polymorphs by enlarging the tunnel insertion and de-insertion layers, by screening with water molecules, to screen this oxygen-magnesium effect. So going to those, and in both cases, the electrochemical process are driven by this known electrochemical reaction, which as here C and A are referred to cation and anion. So then during the insertion and de-insertion in both cases, in this case we will exchange 2 electrons, in this case only 1. During this process, the exchange of lithium will impact the crystal structures or the host structure, and the electron will impact the ionic electronic structure. So what's the common and the difference between monoelectronic and bielectronic process? Is it anionic redox, cationic redox, or is a mixture of both? So to track this, we need experimental evidence, and yesterday during the presentation, that's the characterization is main frame of this Polis process to go beyond the known characterization technique. So let's go now to magnesium system, and with this phase, famous Chevreul phase, some of you know, but I will remember what that means, Chevreul phase. The first Chevreul structure was copper molybdenum sulfide, and this structure is different from punctual metal oxide layers, where the metal is organized in certain cluster with the octahedra molybdenum surrounded by sulfur. And we have like 3 cavities in this structure which can host the magnesium. Cavity 1, 2, which are active electrochemically, and cavity 3, which is not active, but it plays some role, we will see. And during the insertion, we have like 2 plateaus. We can insert reversibly 2 magnesium with about 130 million per gram. And in this structure, there is like 2 kinds of sulfur, 3 coordinated sulfur and 4 coordinated sulfur. And this play a very important role in the following process. And if we go now to this structure, we can see, I will just remember one, like as I say, the ground rule. This structure, this molybdenum needs 24 electrons to stabilize, to have charge neutrality. But when it's empty, it has only 20 electrons. So that's the 4 electrons are brought with the magnesium during the intercalation process. So we can just, what can we learn from galvanostatic like profile? We have 2 polarization. One polarization about 70 millivolts in the beginning, in the first plateau, and very low polarization. So we will learn what does mean in terms of ionic charge transfer. This work was done by Julien Richard during his PhD work. So let's track this by XPS. Let's follow the first plateau. We will go like with first plateau, second plateau, and go back. During the first plateau, if you remember, there is like 2 kinds of sulfur, 3 coordinated, and that's what we can see in sulfur 2 peak, where there is 2 population of sulfur in the red and blue, and there is some surface, subsurface structure. In parallel, like in lamellar metal oxide, that's what we call hydroxide in the surface, there is some similarity. When we start insertion, we can see that the sulfur, 3 coordinated sulfur disappeared, and so we have only 1 population, which is sulfur 4 coordinated, until 1 magnesium. And during this process, the molybdenum stays stable. There is no change. After 1 volt, we can see that the molybdenum starts to work, and then it's reduced from molybdenum 3 plus to 2 plus. And in this case, we have like 2 sites of magnesium. The first magnesium was inserted in the first cavity, and the second magnesium in the second cavity. So by doing GATT, we can see that this polarization is just like, is not the stable phase, it's unstable phase. When we start to insert, there is certain instability inside the cavity, but the real plateau is here. But what we can learn from XPS as well, from magnesium 2p peaks, there is like 2 peaks here, but some people, they can say we can fit with many components, but in this case, we can learn also from Auger spectroscopy, which is another like powerful tools in which we can have fit in XPS. And we can see there is another population of magnesium, which is like closely to metal magnesium. So when we form the first ring and the second ring here, we have certain interaction magnesium here, which has bring this new peak. I will not go to the detail, but we can discuss about this issue. So we can learn that there is like 2 cavities. One is magnesium for the first magnesium and the second magnesium. And what we can see that only 1 sulfur exists, and the structure become more ordered. So I think the powerful, like what we can learn from this structure, it's kind of accordion. When we insert, there is some rearrangement, and the structure can breathe without with delocalizing the charge and sharing the charge between cation and anion in very nice way. So then we can resolve this process in 2 steps. The first one with reorganization of the first sulfur structure and the insertion in magnesium in the first cavity and so on. So the question, what does happen in lithium system when there is like metal sulfide structure? We can learn also from the first materials like thallium sulfide in lithium batteries. So we don't have like a cluster of molybdenum in this case. This is a punctual metal. So in this case, we have two kinds of sulfur. We have sulfur anions, and disulfur anions. When we discharge, sorry, we have first that sulfur is working. There is oxidation of this reduction of the sulfur to have only one population of sulfur, and then the titanium starts to work. So there is this collaborative work between sulfur and titanium. In XPS, the sulfur is very nice materials because the binding shift is about 12 electron volts, so we can clearly see this shift without problem. But in oxygen, it's more complicated in XPS. So what can we learn? Do we have the same process in metal oxide in lithium batteries? So I will take the most successful materials nowadays is like, for example, lithium cobalt oxide, lithium nickel oxide, NMC. We can insert with high capacity and high density, but we have this unsafe zone where we have like electrolyte oxidation when we are above a certain voltage, and we have lattice degradation when we are about certain insertion level. Mostly for several years, we always write this process like this. When we insert or de-insert, mostly the redox process is carried out with the metal. We always forget to write something on the oxygen. We write only on the metal. That's how we write the things. So is there any, what's the role of oxygen in this process? So there is two trends now in the literature. There is what we call cationic redox. That's what so when we de-insert lithium, there is only the metal is working. And when in the system like lithium-rich materials, to explain this excess of capacity, if we take in the calculation only the metal redox process, we can't explain this. So that's why we put a new process, what we call anionic redox. So this anionic redox also should be carefully taken because we will see that neither this nor this it's something in between, what we can see. And it's still, from this, it's still open question. Let's go to lithium cobalt oxide and take some breath and look at what we have learned from literature since Goodenough proposed these materials. In 1992, Delmas group, they showed by XRD that there is shrinking of oxygen-oxygen distance. So that's the oxygen plays some role in this process. By DFT calculation, from 97 to 98, we start to propose that there is a participation of oxygen in this redox process. With bulk materials like bulk technology, like characterization like XAS, we start to make the evidence that there is a co-participation of cobalt and oxygen in the redox process. And recently, there is more claim on the oxygen redox process proposed by RICS or other sophisticated DFT calculation by combining with dynamic mean field theory. So here we have to ask a new question. What is the charge transfer? How can we track this charge transfer with this experimental evidence and by combining experience and theory? Okay, what we learn again also from literature, if we look at the oxygen peak here, during charge and discharge in lithium-rich, we have this new components which are related to some oxidation of oxygen. In Daeron and in 2008, they saw that there is also during charge a new peak here. By more bulk, those two techniques are like surface sensitive, that one can think that are like surface oxide that are not really the redox process driven, but it's just like something in something happening in the surface. But if we look at bulk, more oriented material like technique like RICS, we can see during the chart that there is a new feature here which is oxidized oxygen, and that's work confirmed in other works. And for us, what we decide, to get off with this, like as you know, during charge and discharge, the material became like a new material with like what we call CEI, and I prefer to call it positive solid electrolyte interface, not cathode electrolyte interface, because the cathode can work as anode as well, but anyway. This is ontology. And there is also this surface reduced layer, which are changed from spinel to rock salt. And there is this bulk material. How can we overcome this? By XPS, by doing HAXPS, like hard X-ray photoemission, where we can probe deeper, up to 15, or with synchrotron facility up to 30 nanometers. And additionally, inside the same spectroscopy, we have different probes that bring different depth profile. But if we track the cobalt 3P, we are not probing the same depth if we track the cobalt 2P. So inside the same spectroscopy, you can also do non-destructive depth profiling. And also, we need another ingredient to combine with theoretical calculation. So this work has been done by Roberto Fantin, who defends his thesis this year. And what we choose we work on lithium cobalt oxide thin films, and we cycled up to fully discharged. We know that cobalt, it works safely up to 0.5, but with like C over 20, we could de-intercalate. And as you know, in XPS, there is two approaches. There is the fitting approach, and in this fitting approach, we can do a lot of mistakes, but at least if we have some certain theoretical background, we can try to fit in a very accurate way. What we can learn from XPS that there is two features, except let's say this is spin orbit coupling. We will not talk about that. We just we talk about these two features, what we call the mainline and the satellite structures. As we can see, depending to the materials, we have different satellite structures. So the satellites can give a clear feature about the metal-ligand interaction. So if we look at the spinel phase, the satellite is more intense. If we look at lithium cobalt oxide, we have very tiny satellite here. What we can also take advantage from HAXPS is we can get off of these Auger lines, which disturb the structure, the peak. And usually the broadening of the peak when we fit, we do not take account of this Auger feature, which are buried inside the spectra. Most of the XPS spectra, if we look at the literature, they cut here from here to here. So we do not see these features. But by doing HAXPS, since the Auger electrons are conserved, so the Auger spectra will move out, then we can have a cobalt 2P peak with clean from Auger feature. So we can use it to fit our peaks. And here, by fitting this peak, I will not go to this detail of peak fitting. We took many effects. That's what we call, when we do XPS, we have the structure reorganized through local screening and non-local screening effect. That's what can be explained by the two peaks. And there is also intra-atomic relaxation process, which can be fitted with this and the satellite. By taking this peak model fitting, during the intercalation, we can see a different, the evolution of cobalt 2P peaks. What we can see here, that the satellite picture here, which is representative to cobalt 3 plus, is still there. And we do not see any satellite feature for cobalt 4 plus. So the question, where does go this cobalt 4 plus? If we look at the oxygen peak from XPS and HAXPS. Let's look at first the XPS peak. This is the XPS from lithium cobalt oxide with oxygen of the network and some suboxide. After the intercalation or the insertion, there is a new peak and the shift to lower binding energy. Is it real or just peak calibration? But by doing HAXPS, we can see that this feature is still there. This is not surface oxide. And by doing calculation, we could produce this shift and the presence of two oxygen-like structures. If we want to go deeper in this feature, we moved to some, as I said, what's the rule we fixed. This is also in solid state chemistry perspective. That's how we deal every time when we look at in the schema. That's the Mantiram that he proposed this with there is spin or crystal field splitting, and always we represent this feature like this. And since we don't know how percentage we will put to 3 and 4, we mix everything there and we call cobalt 3, 4, nickel 2, 3, and so on. And we left the oxygen rigid without any reaction. If we look at solid state physics, by taking this oxygen as a punctual defect, there is two parameters, like the Mott-Hobart parameters, which bring interaction between Coulombic repulsion between dd orbitals, and there is also the charge transfer from oxygen to the metallic state. So the XPS in other aspects, that's what we have in XPS. Usually when we do XPS, this is how we can write the XPS spectra. There is the first photoemission process, and there is what I called before local screening, non-local screening, which can express with this wave function, which make a hole in the ligand. So we have two scenarios, what we call positive charge transfer or negative charge transfer. The positive charge transfer when the oxygen bring coupled with occupied state, and negative charge transfer when the oxygen participate to the band gap and send an electron to the unoccupied state. So if we now will go to DFT to simulate our XPS spectra, if we could take classical DFT, which doesn't take account this coupling, we can explain the shift of the peak, but we cannot bring the satellite features. We can't explain because DFT, it's neglect the screening of core hole interaction. That's why we need new approach with ab initio based cluster model simulation. For that, if we look at the XPS, this is our ground state. Imagine this is cobalt and this is oxygen. When we send a photon, we eject an electron, we create a hole here. That's how we can write it in a wave function, like a core hole coupled with d orbitals, and there is a ligand transfer from to compensate this charge, and by compensating this charge we can have the final story. So we can write this with more sophisticated Hamiltonian, and we can draw the XPS features. I will move this. So what we will calculate by the end is the ratio between charge transfer and U interaction. So if we look at the valence band structure for lithium cobalt oxide, we have three features. If we take only a classical DFT, we cannot explain these satellite features here, but with cluster model, we have the partial occupation of oxygen, partial occupation of d orbitals, and the satellite structures. So we draw the picture of lithium cobalt oxide and de-intercalated lithium cobalt oxide. So by screening all U and delta to fit our XPS data, we comes out with the final pictures here to simulate our cobalt 2p peaks after insertion, by using Hagspace. This is simulating Hagspace spectra, sorry. And what we can see that the D5 structure doesn't exist, which is representative to cobalt 4+. We have always D6 structures, so which is representative to cobalt 3+. But how does it work? Let's look at here more parameters. That this is the UDD. This is the UDD value, and here we report the delta value that fits with our XPS data. And the grain line here is only the best fitting parameters. So we can see that when we de-insert lithium, indeed, we remove an electrons from the structures. But immediately, as soon as we remove this electron, the oxygen draw back an electron to the EG state. So that's how we call it negative charge transfer, and by this way the oxygen compensates this charge transfer. So at the end is not cationic or anionic, is more collaborative and self-regulation process. And also something that we have, I think this is for the audience, we always neglect the spin effect, because we found that the best fit was with low spin configuration rather than high spin configuration. People who deal with manganese, they know that the spin are really important to reorganize the electronic structure. But this is maybe someday there is a field of electrochemical spin, electrospin, I don't know how to call it, spin electrochemistry, something like that. And then we draw these final pictures, like just I summarized. So at the end, the charge compensation from different perspectives, there is several, the classical picture, which is cationic or anionic, and there is other picture which is more cooperative technique. So to track this, I think we need new experimental and theoretical technique for capturing the direct and non-direct effects of non-conventional redox process. So here, if what we can learn from lithium, if we go back now to magnesium batteries, how can we screen this strong interaction between magnesium and oxygen? I listed few strategies, but I am not, maybe there are some. Like, let's say there is charge delocalization using cluster structure. That's what we saw with Chevreul phase, with other chalcogenide, sulfur, organic carbonyl polymer. We can do also charge screening using tunnel structure multivalent cathode. For example, polyhedra manganese, vanadium oxide, which has multiple oxidation state. We can also do multi-charge center using organic ligand that can disperse the charge around between metal and ligand. Or we can have also delocalized charge in organic cathodes by flexible molecular framework that can offer in room of functionalization and more freedom of magnesium to move in the system. So with this, I would like to thank you.